Hello everyone. So today we are going to talk about the application of definite integrals. We discuss how to use integration in the calculation of area bounded by curves, in the calculation of volume solid of revolution, then finally how to use integration in the calculation of arc length. Let's start with the calculation of area bounded by curves. The area of the region bounded by the curve of a function fx x-axis, the unit x equal to b, is given by the formula area is equal to integral from a to b fx dx. So this is the formula we use when we are looking for the area of the region bounded by the curve of a function. The region you see here shows the area enclosed between fx x-axis, the unit x equal to b, and the area will be equal to the integral from a to b, then fx dx. When you are finding the area under a curve, so before you look for that area, you have to follow the steps below. You have to show the region enclosed between the curves. Then you have to look for the boundaries, the limit of integration. Then you have to set up the definite integral and then you calculate it. Example number 1. Let's find the area enclosed between the graph of the function fx is equal to 2x plus 1, x-axis line is x equal to 0 is equal to 1. As you can see here, we have the graph of the straight line 2x plus 1 between 0 and 1. This shaded part shows the region between this straight line x-axis line is x equal to 0 is equal to 1. And then the area is equal to the integral from 0 to 1 to x plus 1 dx. So the integral to x, as you all know, is equal to x squared. Then the integral of 1 is x. Then you replace there 0 and 1 as lower and upper limit. So the answer will be 2. So the area of this region is equal to 2 square units. Discuss how to look for area bounded by two curves. The area enclosed between the curve of the function fx and that one of gx is given by area is equal to the integral from a to b fx minus gx. You can see here we have the region included between fx and gx. So here you have the area included between x-axis and fx, this one, and then we have the area included between gx and x-axis, this one. So the area included between f and g is equal to the integral from a to b fx minus the integral from a to b gx. The reason at why we are taking fx minus gx is because fx is the upper curve of this shaded region and gx is the lower curve of this shaded region. So the difference will give you the area included between fx and gx. If function changes over the interval, we may split the interval into sub-intervals on which f is either positive or negative. So after splitting the interval into sub-intervals, you can calculate the definite integral of each function in a given subinterval. Then when you are done, you add all positive integrals and all negative integrals. But remember, the area which is negative doesn't exist. That's why finally, when you are looking for the total area included between curves from A to B, you sum all the positive integrals and the opposite of all negative integrals. So remember, when you put negative there, for all those negative integrals, you'll end up with positive. Then the sum will be the area of the given region. So we are going to do an example here. Let's do this example. We are going to look for the area between gx and fx. Gx is this one, and you have fx which is equal to 2x squared minus 2x. First of all, let's calculate the intersection of these two curves. We have to equate y is equal to x power 3 minus 2x plus 2, this one, and the 2x squared minus 2x, this one. So after equating them, we are equating these two functions because we wanted to look for the limit of integration. So after solving the equation, we will get x equal to 1 or x equal to negative 1 or x equal to 2. So here we have our limit of integration. Let's see how we can make the graph of these two functions, and then we see the region included between the two. As you can see, we have the graph of gx, this one, and the graph of fx, this one. So we have the limit of integration, the other values we got before, which came from the intersection of between two curves. We have negative 1, we have 1, and we have 2. So as you can see, we have the region included between two curves between negative 1 and 1, this one. So we have this region, and we have another region from 1 to 2. So the area between f and g from negative 1 to 1 is equal to the integral. Let's do it. So from the previous slide, we saw that over the interval from negative 1 to 1, the graph of g is above the graph of f, and from 1 to 2, the graph of f is above the graph of g. So the area of the part of the plane between the two curves over the interval from negative 1 to 1 is equal to the integral from negative 1 to 1 of x power 3 minus 3x plus 2, this one, minus 2x squared minus 2x dx. So the reason why we are taking x power 3 minus 3x plus 2 minus that one of 2x squared minus 2x is because the graph of g is above the graph of f. So g is the upper curve and f is the lower curve. So we are going to integrate as usual. The integration here will be x power 4 over 4 minus 2 over 3x power 3 minus a squared over 2 plus 2x from -1 to 1. So we are going to replace their upper limit and lower limit using the fundamental theorem of integral calculus. So here the final answer will end up being 8 over 3. So basically this is the area of the region included between these two curves, but from -1 to 1. Remember that you have another part from 1 to 2. So that part, its area is the integral from 1 to 2. So fx is the upper curve and gx is the lower curve. So here we are going to interchange, and we take 2x squared minus 2x, and then minus x power 3 minus 3x plus 2. This one is the lower curve. Yes. The area of the region from 1 to 2 will be equal to the integral from 1 to 2 then of negative x power 3 plus 2x power 2 plus x minus 2 then dx. As you can see, after calculating, this integral will end up with this one, negative x power 4 over 4 plus 2 over 3x power 3 plus x power 2 over 2 minus 2x from 1 to 2. So after calculating, the area of the region from 1 to 2 will be 5 over 12. So remember that the area we are looking for is formed by the area from -1 to 1 plus the area from 1 to 2. So we have that one of the region from -1 to 1, this one, and this one from 1 to 2. So the total area will be equal to 8 over 3 plus 5 over 12, which will end up being 37 over 12. So the area will be equal to 37 over 12.